Okay, let's go back in time. The date is June 30th, 1908. Over a remote, empty stretch of Siberia, the sky just explodes. It was one of the most powerful and, frankly, one of the most baffling cosmic events in all of recorded history, a mystery that would take scientists over 100 years to finally piece together.
Can you even imagine that? You're going about your day and suddenly you look up to see a second sun ripping across the sky. That's exactly what witnesses described. The light was blinding. It was followed by this wave of heat so intense, people said it felt like their shirts were literally catching on fire, and they were 60 kilometers away.
And then came the explosion. It was just monstrous. It flattened 2,150 square kilometers of forest. Now, that's just a number, so let's put it in perspective. That is an area bigger than London, bigger than New York City. We're talking about an estimated 80 million trees, all knocked over like they were matchsticks, pointing away from a single, terrifying central point.
But here's where the story gets really weird. When scientists finally made their way out to this desolate landscape, the scene only made the mystery deeper. The destruction was obvious, for sure, but the cause? Well, that was anything but. It left these central puzzles that would just baffle researchers for decades.
Think about this for a second. The energy release was something like 1,000 times more powerful than the atomic bomb dropped on Hiroshima. An explosion of that scale, that magnitude, should have left behind a massive crater. But when they looked, there was nothing. No hole, no impact site, just miles and miles of flattened forest. So how is that even possible?
The first real attempt to solve this mystery wouldn't even happen for almost 20 years, when this really determined Russian mineralogist, a guy named Leonid Kulik, finally managed to reach the site.
Kulik was absolutely convinced he was going to find a giant iron meteorite. I mean, it made sense, right? So he organized these grueling, difficult expeditions into the swampy terrain. He found the pattern of the fallen trees, which confirmed the epicenter. But the thing he was really looking for, the impactor, or the crater it made, it just wasn't there. He came up completely empty-handed, and the mystery only got deeper. So, with no big rock to analyze, scientists had to get a lot more creative. The investigation basically shifted from a physical search to a chemical one. They started hunting for microscopic traces, sort of like a chemical fingerprint left behind by whatever this mysterious object was. And the key to this whole chemical search was an element called iridium. You see, iridium is incredibly rare here on the Earth's crust, but it's super common in asteroids and comets. So think of it as a calling card from space. If they could find a spike of iridium in the soil layers from 1908, that would be definitive proof that something from space hit us. So, researchers analyzed samples from a peat bog, and sure enough, they found the iridium signature they were looking for. But they also found something else, something weird. An unusually high amount of carbon. This meant the carbon-to-iridium ratio was way, way higher than what you'd expect from a normal stony asteroid. It pointed to a completely different kind of culprit, something much richer in carbon, maybe even a comet. Now, this strange chemical signature was a huge clue, no doubt about it, but it still didn't explain the biggest puzzle of all. How do you get that incredible level of destruction on the ground without leaving a crater? The pieces still didn't fit. The next huge leap forward didn't happen until a full century after the event. This is when powerful new technology came into play. All of a sudden, scientists could treat the site like a microscopic crime scene, analyzing soil samples from the epicenter with incredible, almost unbelievable precision. And under the microscope, a whole new world of evidence just appeared. They found these tiny iron-rich spheres, little bits of melted quartz and feldspar, even tiny carbon spherules that were formed from instantly incinerated plants. But the most important discovery of all? Minerals that had been physically, fundamentally altered by immense force. The real smoking gun of a cosmic impact turned out to be something called shocked quartz. Now, this isn't stuff you find lying around. To create it, you have to subject ordinary quartz crystals to pressures that are so extreme, so violent, that their internal crystal structure gets permanently scarred. It leaves this unique, crisscrossing pattern, and it is definitive, undeniable proof of an impact from space. And the Tunguska samples had it all. Those telltale microscopic scars, what scientists call planar deformation features. They found fractures inside the quartz grains that were literally lined with glass, even coatings of melted silica on their surfaces. This was it. Undeniable proof of both incredible pressure and incredible heat.
So just how much heat are we talking about here? Well, based on those tiny melted quartz spheres they found, the ground was momentarily exposed to temperatures over 1,710 degrees Celsius. I mean, just to put that into perspective, that's hotter than volcanic lava. And it happened in a flash. Okay, so now all the pieces were finally on the table. We have the immense energy, we have the no-crater mystery, but we also have definitive evidence of extreme heat and pressure right there on the ground. For the first time, scientists could build a computer model to see what really happened that day.
Let's walk through it step by step. So a 60-meter asteroid screams into the atmosphere and it explodes in a massive airburst about 6 kilometers up. But, and this is the absolute key, the explosion itself isn't the end of the story. The downward blast from that explosion acts like a giant cannon, firing a plume of superheated vapor and smaller fragments down toward the ground at over 2 kilometers per second. It's this swarm of fragments that actually strikes the surface, delivering the insane heat and pressure needed to melt minerals and create that shocked quartz, all without a single big rock ever hitting the ground. They call it a touchdown airburst, and it solves everything.
And just like that, the touchdown airburst theory solved the century-old mystery. But you know, understanding what happened back in 1908 isn't just about closing a historical cold case. It's actually a critical warning for our future.
See, Tunguska wasn't some kind of freak, one-off event. In 2013, a much smaller but still incredibly powerful airburst happened over Chelyabinsk, Russia, and that injured over 1,000 people. And then, just very recently, in 2023, an asteroid named 2023 NT1 gave us a very, very serious scare.
This asteroid, 2023 NT1, was estimated to be somewhere between 30 and 60 meters wide. That puts it right in the same size category as the Tunguska impactor. It had the potential to unleash the exact same kind of city-leveling explosion.
And here's the part that should really give you chills. We didn't see it coming. Our planetary defense systems, all of our telescopes, only spotted this Tunguska-sized object 2 days after it had already zipped right past Earth. It came at us from the direction of the sun, which is a well-known blind spot for us. So at the end of the day, we now understand how a Tunguska-level event can happen, and we know for a fact that they are a real, reoccurring threat. We just got lucky in 1908 that it happened over a remote, empty wilderness. And that leaves us with one pretty unsettling question. Where will the next one be?